In this video, I want to showcase how to solve problem 3.6 from your textbook using nodal analysis. Problem 3.6 gives us this schematic here, and we're asked to find the voltage V1, which is the voltage dropped across this 10 ohm resistor in the middle. What we're going to do is assume that our bottom node is our reference or our ground node, so this entire bottom of the circuit is ground. And then we will also assume some directions for currents flowing through each of the resistors. It doesn't really matter what our assumption is so long as we're consistent in our math. So I'm just going to assume that the current flows through this 5 ohm resistor left to right, through the 10 ohm resistor left to right, through this 10 ohm resistor here in the middle downward, and through the 4 ohm resistor left to right over here. And you'll also notice that we only have one non-reference voltage node that's not an obvious voltage. So here we have another node over here, but because we have this 10 volt supply, we know if we're choosing this bottom as a reference, this has to be 10 volts. That's by definition what this voltage source does for us. And also over here, this node is 20 volts of potential because that's exactly what this 20 volt voltage source does. So there's really only one unknown voltage, and that is V1. And so what we're going to do is we are going to develop equations for all of the currents entering and all of the currents exiting V1. And so if current is entering, we're going to have that be positive, and if current is exiting, we're going to have that be negative. So first of all, the current through this 10 ohm resistor up here at the top is going to be 10 volts, that's the potential over here, minus V1, that's the potential over here, divided by 10 ohms. So we're just using Ohm's law to figure out the current. And to determine what we're going to subtract, we're going to start with the node voltage on the left and subtract it from the node voltage on the right. In general, based upon how we're drawing these arrows, we're going to go from the end of the arrow without the arrowhead on it minus the potential where there is the arrowhead. So 10 volts of potential over here, V1 over there. We're going to add to that the same voltage drop divided by this 5 ohms. So that's the current through both of these parallel branches here. And then we have this current leaving. So we have minus V1 divided by 10 ohms. I could have said V1 minus 0, but we can just leave off the minus 0. And then we also have this current leaving through the 4 ohm resistor. So that's a minus because it's leaving. And we have V1 minus 20 volts over 4 ohms. So if we have all of these fractions, in order to solve this, we'll find a common denominator. So a common denominator of 10 ohms, 5 ohms, and 4 ohms is 20 ohms. So if we scale this up and put everything over 20 ohms, here we've got to multiply this numerator by 2. Here we've got to multiply this numerator by 4, multiply this by 2, multiply this by 5. And then we're also over here for this subtraction, we're distributing this negative. So that's why this ends up being a positive. We have minus a negative number here, so we end up with a positive 1000 volts. And so all of this still sums to 0 amps. That's what Kirchhoff's current law tells us. And so now we can multiply both sides by 20 ohms. So we have 0 amps times 20 ohms gives us 0, but now the units change to volts. And if we take all of our like terms and gather together the volts that we know and gather together the number of V1s, we get 160 volts minus 13 V1 equals 0 volts. And so we just do some algebraic manipulation, and that tells us that V1 is equal to 160 divided by 13 volts.